All right, good morning, everybody. This is the last lecture we're going to be talking about compression members, so it seems like this went by a little bit quicker perhaps than tension members, which seem to come up every other day. So far we've talked about pretty much everything on the slide. We know how to calculate compressive resistance using the first equation. Based on the third equation, BEL over T, whether or not it's less than or equal to that limit that comes from table 1 in the handbook, we may or may not have to calculate an effective area, which we talked about in lecture 24. And then in lecture 25, we talked a little bit more about when we might be using different values of K or L to calculate the elastic buckling strength, and when the different global modes of buckling would tend to govern for different effective lengths for weak, strong axis, and torsional buckling. We also talked very briefly about the serviceability limit state to keep things efficient and straight. We want to make sure that the effective length ratio, KL over R, is less than or equal to 200. About that briefly in the introduction lecture to compression members. So now that we know how to calculate compressive resistance, we have an idea about how different compression members may or may not buckle in our structures, whether they're used as columns or a compression brace and a braced frame. We know how to calculate strength, we know what to look out for, and for us to start thinking about compression member design. Okay, so how do we pick something that's going to work for the factored compression force that we calculate on a column or on a brace? What do we need to do that's going to be efficient but safe to satisfy the ultimate and serviceability limit states? Okay, so just to recap briefly here, we know that there are two potential curves that we might consider when compressive resistance of different compression members. Some of our sections might not have any residual stresses, and so in that case we're calculating with a certain n value. Most of our sections will have residual stresses, and so that reduces the strength a bit. We use a different n. And if you don't know if your section has residual stresses or not, you just use the lower curve. So we also looked at modes of global buckling, and this is going to be an important one for today. We talked about when weak axis, strong axis, or torsional buckling might govern the compressive resistance of a member. And what's important to see here is, if we multiply everything here through by whatever AFY is equal to, basically these curves give us the answer for a compressive resistance for a bunch of different effective lengths. Okay, so if we know the answer, for example, a W250 by 33, we know the answer for resistance about the different modes of buckling for different effective lengths. That's going to make our job easier, and I'll come back and talk about that momentarily. The thing that's most important to take away from this is that for simple columns that have the same effective length for strong and buckling as well as torsional buckling, it's always the weak axis buckling that's going to be governing the strength of that member. Then the handbook helps us select members mostly with that in mind, but there's also a tool that we can use from time to time to consider strong axis buckling as well. The last thing we looked at were these table 1 requirements, and so for flanges sections or webs of wide flange sections or walls of HSS sections, we had width to thickness ratios for the plates in the cross section meet these certain limits. Otherwise, we had to start reducing the effective area and compression, and we talked about how to do that calculation. What we're looking at is selecting members, and so after this you should be able to identify which shapes make effective compression members, columns. The first thing about good design is knowing which sections are going to tend to be more efficient. Okay, so we talked about that a little bit for tension members. Flat bars are efficient, HSS sections tend to be efficient, WT sections that are cut from stocky sections tend to be efficient, and there are just certain shapes that we use more often as compression members or beams or tension members, and we'll see what works to columns. Should be able to navigate the column selection tables in the CISC handbook. Does anyone have their CISC handbook here with them this morning? The one day no one has it. I also don't. Do you have it? I might ask to borrow it in about 30 minutes or so. That's okay. So you should be able to navigate those tables, and I'll show you how to do that again with some shoddy camera work, but it's worth it. And ultimately, the goal is to select the least weight section that's going to satisfy the compression limit states for the problem that we're dealing with. Okay. Does anyone have any questions about why these three things might be important before we get into the technical material for the morning? Okay. So we talked about designing tension members quite a while ago. We tried to back calculate the area that would be required, right? So we looked at gross section yielding. We looked at estimating the net section in terms of the area removed for bolt holes if we're bolting and the shear lag effect. And what we could do is we basically would back calculate the effective area or the total area in the section we need to satisfy the tension limit states. I want you to take 30 seconds or a minute and think about how, based on the equations here, we might try to select a compression member that might work. So for tension members, we calculated an area, found a section with a minimum amount of area that would work. How can we do the same exercise or a similar exercise for compression members? And I'll leave these equations up here to give you a little bit of time to think about it. About a minute, talk with the person next to you. How are we going to pick something that's going to work for compression members? Okay, we'll come back now. I've heard some decent discussions. Does anyone want to share from the discussions you had with the group or people next to you, or even just the internal thoughts and internal monologues going on in your own head? Anyone have any ideas how we might pick a section that will work as a compression member? Those of you who did talk about it, do you think it's as simple as what we did for picking a tension member previously? Probably not, right? Why? Anyone want to share why it's harder probably to pick something for compression members than tension members? Well, there's a lot of moving parts here, right? For tension members, we basically just had a bunch of stuff that were based on area, right? We had phi A F Y, and we had phi U A N E F U, right? And I mean, sure, we needed to know a little bit about what the connection looked like, and so we might need to estimate A and E, but we could estimate reasonably. This is just a straight shot for the area that we need if we know Fy, and phi is always the same. So that was pretty straightforward. When we look at the compressive resistance expression, pardon me, there's a bunch of stuff going on, right? We a similar term here in the numerator, we have phi A Fy, but if the flange of HSS are quite thin relative to the width, then we're going to have to start reducing the area. And so it's not just a calculation, it's an effective area calculation. That depends on whether or not local buckling is going to be important in calculating the resistance. Not only that, but it's inversely proportional to this lambda term, right? And then we've got n, and so all this sort of crazy in the brackets here, right? Lambda is equal to the square root of Fy Fe. Fe, if we're looking at torsional buckling, is this crazy expression, but we did at least say, well, for the it's going to be something like Fey, so we might do pi squared E over Ky Ly squared. Right, so at least if weak axis buckling is going to govern, we at least know it's going to be something like this. We need to know the length of the member, and that's fine. We probably know that. We need to know the effective length factor, and that's okay. We can probably know that. But that's RY, right? So we need to know an RY. We need to know an A. We need to know how thin the flange and the are relative to their plate widths. And so there are a lot of moving parts here. There's no straight shot to calculate A. We could figure out A, and we might be able to figure out like a KL over R ratio that works for serviceability limit states. But the message I'm trying to convey here is it's not a simple back calculation. This is an inverse problem that's not as simple as the problem we had for tension members. We're going to see in a minute that the easiest thing for us to do is calculate what the answer for a bunch of different sections. And so, for example, we can, for a certain effective value, let's just say KL was equal to 2,000, we could, for a W250 by 33, calculate what that resistance is. And we could say, okay, well, that's the answer for compressive resistance for a W250 by 33 of 2,000. This is the answer for the compressive resistance of the same section with an effective length of 25. And we can do the same thing for a bunch of different effective lengths. And if we do that, we basically have a bunch of answers, right? We could say, well, for our effective length, we could come and we could look up the answer for compressive resistance for this particular and see if we have enough strength. And what we're going to see is that in the handbook, there are some tables that are watermarked green on the edges. If you have your handbook, you can see that. And basically what the handbook gives us is tables give us the compressive resistance for a W250 by 33, a W250 by 37, all of the cross sections that are used columns. The tables tell us what the answer is. Okay, so that means two things for you. One, it makes your design life easier because you can go see what the strength is. And two, if you ever have to calculate the compressive resistance of something in this course, you can check the answer, right, for the most part. So they are discrete values of length. It's not continuous like the curves that we have here. For intervals, usually in every 500 millimeters or every 1,000 millimeters, we have compressive resistance values that are tabulated for us in the handbook. So the first question that comes up is, what kind of section is to be used as a column, and why is a W250 by 33 shown in this particular instance? I showed a time ago, lecture 2. Also, I think I showed it more recently than that. I can't quite exactly remember. But a bunch of different types of wide flange sections. There are W200s, there's 410s, there are 930s, a bunch of really tall beams, narrow, and a bunch of really short beams that are wide. Which of these two sections do you think is most likely to be more efficient as a compression member? The one on the left or the one on the right? Left-hand side, right? And the reason for that is, if you look at these two sections, one is taller than the other, but the mass per meter is basically proportional to the cross-sectional area. These two sections have the same area, right? So the areas are equal for these two sections. And if you were to do the I calculations, quite big, but IY here is small. And if we looked over here, X for this section is less than the IX for the one on the right, but IY is greater for the one on the right. Okay, so we already talked about the fact that weak axis buckling is more likely to govern. The axis here is stronger than the strong axis here. It's more likely to buckle about the weak axis, so when we calculate R, KL over R is going to be much bigger for this, which is going to drive our resistance down compared to this one. So looking at wide flange shapes, we want to pick sections that are wide relative to their height. And basically that means we want to pick them to be really small. Okay, so the handbook is not going to give you compressive resistance values for a W410 by 46, because no one should use that as a column. But they will give you compressive resistance values for the W200 because we do use those as columns. HSS are also very effective and very efficient There's a lot of steel area far away from the centroid of the cross-section, and they're metric. A wide flange section, for example, IY is going to be less than IX. And so if you think about the use of steel as a column or as a brace, use of steel isn't as efficient as it could be because it's going to buckle about the weak axis rather than the strong axis. IX and IY more comparable, which you can do when you have a square HSS or a round HSS. Compressive resistance around both axes becomes the same for these types of shapes, and that helps us use use the steel more effectively compared to something like an HSS or a wide flange section. Wide flange sections usually have bigger second numbers. We can get really, really, really heavy wide flange sections, and so we tend to use these as columns. From time to time, though, for light loads, we'll use square HSS sections for columns, sometimes round HSS for columns. Typical for us to use these as compression braces when we have braces carrying either compression or tension. So these pages, or these tables that show you the compressive resistance, they look something like this. Note a couple of things in the table. One, it tells you what Fy is. And so as I've said before, time and time again, for wide flange sections, we don't make these in Canada. It's not that we can't, we just don't. I guess we haven't found an economic incentive to make wide flange sections in Canada, so we import them from the US instead. And so when we import them, we usually get an ASTM grade, either A992 or A42, grade 50, which is 50 KSI. And so when you see the tables here, they're going to be using the 345 MPa value for yield strength. And basically what they're plotting here is they're telling you what phi A Fy plus lambda to the 2n, the 1 over n is for all these different sections. And they're basically distance for different values of effective length. Okay, so basically this is another section of the handbook. A bunch of 310 values. So W310, if you zoom in to the top, it's going to say W310. You've got 79. Basically, they're going to get heavier and heavier as we go from right to left. The compressive resistance values for the same value of effective length go up. Okay. What this should tell you is that when you're looking for a section, you want to flip all the way to the last set of tables. That will be your W250 or your W150 or 100s. They're going to be really weak, but you're going to want to start at the first section. And basically, as you move from left to right, you get stronger. You have more steel. And the goal here is to pick the section that's going to have the smallest second number that will work so that we use the steel as effectively as we can. Okay, so I'm going to show you in a minute how to use that in an example to pick some different sections. Example building. The other thing I'm going to say here is that these are all based off of, maybe I'll get you to answer this, think that these values represent torsional buckling? Do you think they represent strong axis buckling? Or that they represent weak axis buckling? Weak axis buckling. This is the compressive resistance. If you go through the same exercise, use an effective length of 4,500 and use Ry to calculate FEY and then calculate lambda and the compressive resistance, you're going to get more or less these same numbers. They round them to 3, but might be slightly different than what's shown, but they'll be the same at least to the 3 significant digits. These are all compressive resistances, right? And that's reasonable because for our simple buildings, as we had said before, especially for end sections, it's always going to be the weak axis buckling mode that will govern the strength for the same effect. So that's helpful for our simple compression members, and from time to time we need to, 95% we're using simple compression members. But there's also from time to time a situation where we might end up looking at the strong axis, right? If we have a multi-tiered braced frame like I showed last time, the axis is usually going to be oriented so that it's braced by the beam against buckling outward, so it's going to buckle in between. This is not braced against buckling along the full height of that column. And so we're going to have something that goes like this. This is the weak axis that does something more like this. And so the question is, what do we do? What do we do for the situation we have a length, for example, Lx that's equal to 2 Ly? Book help us deal with situations where we also need to pick a section that's going to work from a axis buckling perspective. We will remember at least that Fex squared E over Kx Lx over Rx squared, and for Fey, that's pi squared E over Ky over Ry squared. So we'll see here that the only thing to the calculation of Fe, we've got K and Ly. Let's assume here Kx is 1, Y is 1, but Lx is twice Ly. How could we figure out what the values of Fe might be here? Basically, if this is equal to, maybe I'll rewrite this slightly. So this is basically, no. Is that what I want to do? I'm not sure exactly what I want to do. I think I'll write it like that. This is pi squared E over Lx over 2, perhaps, 2Ry squared. And this would be pi squared E over Lx over Rx squared. Basically here, if we were to look at the tables, we might use Ly to figure out what the effect of the tables to get a compressive resistance. If we're looking at Rx and the strong axis buckling mode, the difference here is that, well, of course, Lx is twice Ly, but the only other thing that comes into the here is the R value, right? Radius of duration for X, radius of duration for Y. And what it's going to give us here at the bottom is it will tell us what the ratio of Rx to Ry is. How do we use that to our advantage? Well, if we know what the effective length is for strong axis buckling, in here and actually use the Rx over Ry ratio to modify the effective length. Over here, if we're looking at Lx and we want to know how to use the table to get the strength, what we're going to do basically is we're going to say, okay, Kx Lx over Rx, we're going to take and we're going to multiply it by the Ry over Rx ratio. Do that, then we can get the strength associated with the modified effective length. And what I mean by that is, let's just say, I'll do all this stuff for now. Let me get rid of this. Let's just say, for example, Lx equal to 8,000 millimeters. Ly is equal to 4,000 millimeters, twice Ly. What we're going to do in the table, if we want to figure out what the corresponding strength is from the handbook, we're going to look for a value of KL, which is Lx multiplied by Ry over Rx, or we can simply say Lx divided by the Rx to Ry ratio. So what does that mean? Well, if we go back to this table here, and we say, okay, we're looking for an effective length of 4,000. Let's just use a W310 by 179, for example. If we wanted the weak axis buckling strength, then we would look straight at the weak axis buckling strength is going to be 5,710. If we want to find the strong axis buckling strength, well, that's going to be a little bit more difficult, but not too much more difficult. We can come down here to the Rx over Ry ratio. We see here we've got 1.76. For the strong axis buckling was 8,000. And so what we're going to do is we're going to look for a strength. That's 8,000 divided by 1. And so we're going to look for an effective length of 4,545. Unfortunately, it's not there. But the closest value is 4,500. Why is my eraser not working here? eraser. Oh, that's annoying. So, okay, my marker works, but the eraser doesn't work. Let me back out here a little bit. Oh, I'm just ruining my iPad, I think. Apparently, I'm pushing the iPad to its limits. But what we can see, we've got, for the 4,000, we've got 5,710. And for strong axis, being close to the 45-45, the strength for buckling about the strong axis is 5,340. Okay, so just because the tables are meant for weak axis buckling based on the effective length, we can just take the strong axis buckling length and we can modify it by the Rx to Ry ratio, and we can still use these tables to quickly identify what the compressive resistance is likely to be for that kind of situation. So we've talked a little bit about what sections make good compressive resistance members or columns or compression braces. We can see that it's not as simple for us to solve the inverse problem to figure out what section would make the best compression member. But we have tools in the handbook that can help us pick sections that will be relatively efficient. We can pick based on weak axis buckling, which is going to be the case 95% of the time, but we can also check strong axis buckling based on the Rx to Ry ratio. Does anyone have any questions about any of those concepts before we continue on? Katie. Mm-hmm. 5,710 would be the weak axis, right? So basically, I hope my iPad's still working here. It is, kind of. So for the strong axis buckling, it's buckling something like that. Axis is doing something like this, right? If we were to use Ly here, like the tables are based on Ly. That's what they're based on weak axis buckling. But all the calculations ultimately are based on lambda, right, which is the square root of Fy over Fe. Fe only depends on the KL over R ratio, right? I'll erase some of this other stuff here. Right, Fe is pi squared E over KL over R squared, right? On the KL over R ratio, but when we calculate Fe, we're calculating this with Ry. Give us the compressive resistance based on Ry. They don't give it to us based on Rx, but all we need to do is figure out what the KL over R ratio is for Rx. And if we know what the KL over R ratio is relative to that for weak axis buckling, right, this is over Y, we want it perhaps for KL over Rx squared, right? The KL over R is slightly different, and basically what that means is we just need to change what value of KL we're looking for. Ratio of Rx to Ry, and that's what the ratio is given to us in the handbook for. Okay, so it's just we're modifying the effective length based on the KL over R ratio that goes into calculating Fe. I know, it's a little bit convoluted, like why are we changing effective length for the strong axis? We're not changing the effective length for the strong axis. We're making the effective lengths equivalent between weak axis and strong axis buckling so that we can just use the tables to basically come up with a fudged number that gives us the strong axis buckling resistance. Anything else? Okay. Some other things to be careful of when we're doing these kinds of activities. Hollow sections, remember, there are a bunch of hollow sections. A500 sections, you'll see as a watermark, A500. The areas are 10% smaller because the wall thicknesses are taken as 90% of those given to us. Okay? Class C shapes versus Class H shapes, both G4021 steel. What's the difference again between Class C and Class H? Why would we have different tables giving us compressive resistance for Class C instead of Class H, HSS? Why do we need two sets of tables? Well, we'll perhaps remember that the compressive resistance depends on the value of N. Class C sections are cold formed, not stress relieved. They have significant stresses, and so we use an N value of 1.34. Class H are heat stress relieved, they're annealed, so the stresses go away. So class H, HSS, we use a value of 2.24. So the strength is going to be higher for class H than it would be for class C. Okay? So when we look at the tables, you have to make sure that if you're asked for the compressive resistance or if you're asked to specify an HSS that's class C versus class H, you have to use the right tables. If you want to be conservative and you say, oh, I'm going to specify class H, but I'm going to get class H, you can use class C. But if you specify class H, design it for class H, but get class C, then you're in trouble because the strength is 25% smaller depending on what the effective length of that section might have been. Okay, so these shapes, you have to look at the watermarks to make sure you're selecting from the right classification and grade of HSS steel. Otherwise, you can get yourself in trouble, and that's why they're watermarked in the background. Last thing I'll say is about double angles. Double angles, we also have some stuff provided. Basically, it's going to give us the actually two values. I don't know why they don't do this for us for any four different effective lengths, both the Y and the X-axis buckling resistance. Part of the reason for this, I guess I need to go down here. If we look at the axes, buckling about the X-axis here is buckling about the axis of asymmetry. That's going to flex purely downwards, and so it's only going to be flexural buckling. But axis buckling, it's buckling about the axis of symmetry. That's when we start to get the coupling of flexural buckling and torsional buckling. Okay, so for double angles that are asymmetric about one axis, basically we've got buckling about the asymmetric axis, which is purely flexural buckling. Buckling about the axis of symmetry gives us flexural torsional buckling, and that's why I guess in this case they give us buckling for the two axes, because one includes that coupled mode of flexural torsional buckling. And so we wouldn't be able to just use the Rx over Ry ratio here because, well, flexural torsional buckling is more complicated than that, and so we can't just fudge the Rx over Ry ratio like we did for wide flange sections. Okay, so to summarize briefly, we have lots of different tables. Most of them are for wide flange sections, and we're going to focus on that shortly. When we have wide flange section tables, we can do it for strong or weak axis buckling based on the Rx over Ry ratio. Some of them are for HSS. It's pretty much the same thing, except you need to be careful about the class of thing. You'll have watermarked values for C or H or A500 to help make sure that you're picking from the right tables. And it's pretty common to use double angles back to back as compression tension bracing. These ones have coupled flexural torsional buckling about the y-axis, and so we get flexural buckling values for x, flexural torsional buckling values for y, and we forget about the Rx over Ry ratio thing for double angle sections. Does anyone have any questions about that before we proceed to our example? Okay. So we haven't talked about our building for a little bit, because we see it when we calculate loads and when we design things. We have this building that we've been looking at from time to time, way back in lecture, I think it was 6 actually, in snow and rain loads. We had done this example where we took the live load for occupancy and for minimum roof live, and we took the dead loads, got our individual loads acting on the structure, and way back in lecture 10, you had actually done this example for me in the Pull Everywhere question. We're looking at calculating the factored compressive force acting on our column, and it was pretty easy for us to see that that was going to be based on 1.25 1.5 live plus 1.0 snow. And we'll remember here that because we're including the full load in this combination, when we do the live load part, we ignore the roof live load, right? So ignore the LR part. That was 1.25 times the dead load, which was 1355, plus 1.5 times the live load, excluding the roof live, which is 286, plus the snow, which was 244. And if we did that, we get 2,357 kilonewtons as the factored compression force acting on that column. So we had the dead loads and the live loads and the snow loads on this column from lecture 6. We have the factored compression force from the load combinations we have to consider in accordance with the NBC. And when we put all those things together in that way, we get a factor of force acting on that column of 2,357. Our goal now that we know enough about compression members is to reinforce the concepts we've been talking about so far, and we want to pick a section that's going to work here for us to resist this 2,357, and we want to do it with the least amount of steel possible. Textbook, Kristen, quickly. Thank you, appreciate it, nicely tabbed. Anyone who's writing their exam, tab your book. Similar to that, it helps you go quickly to the pages. I haven't talked much about that so far, but use this as a good example to quickly find things that you want. So basically what we're going to do is we're going to go to the green tables. We are going to pick a W section, okay? Columns are often W sections if you have a structure that's more than just a couple stories tall. It's usually too much load on an HSS to make that work. So we've got a 4-story building here. We're going to pick a W section to work. And this is where I start my shoddy camera work. But we'll go through this process together based on the sections that are available to us. Okay, so let's try this. Remember where my camera is. Okay, so the first thing you do is you open the tables, right? So the green edges are the wide flange section tables, or I guess all the section tables, right? Some double angles, single angles. We're not going to talk about that in this class, but we're going to have some A500 sections. See the watermark. Class H sections. See that watermark. And Class C sections, right? See that watermark. The first page of wide flange sections you're actually going to see is also watermarked as A913 grade 65. What you're going to see there is we want to be careful because that is a completely different yield strength, right? This becoming a little bit more common to use higher strength steels, but in our 345 or grade 50 steel, we want to make sure that we're not unduly requiring the steel fabricator to procure some A913 structural steels. Okay, the first page of wide flange sections, that's grade 50, right? We can see there, grade 50, 345 MPa. And we've got the smallest sections available to us to start, W250, W200. And we'll remember that the effective length for our column, maybe I didn't put this in here yet, but I will quickly go back to the slides. Right, we'll remember that L, right, is 4,500 millimeters. What value of K should I be using for this calculation, do you think? Probably 1, right? I showed you in lecture 25 on Monday. You know, basically we're looking at the bottom column here. It is somewhat connected to a footing, but we've got simple framing at the top. Maybe we could use 0.96 as K, but I'm not going to deal with the nomograph stuff. And so I'm just going to use K as 1. And so that tells me the effective length factor I'm looking for is 4,500 millimeters. Okay? So I need to find in the tables a section that will have a compressive resistance that's big enough based on the effective length of 4,500. Okay, so basically I'm going to come down here. Here's 4,500. Will a W200 by 42 work? Will that work? Got us at least. Okay, no, thank you. At least one person shaking their head. 624 kilonewtons, that's nowhere near enough, so that's not going to work. Basically, we just keep going back, and so we've got some more W200s. 2010, we're getting close. Oh, and then we get to 250s. Okay, so there's no W150 that's going to work. There's no W200 that's going to work. And so we need to work our way up in size. So we've got W250, and we come across. This one's really close, W250 by 89. That's 2300. Unfortunately, we need 2357. So that's close, but it's not going to quite cut it. If it was 2350, I'd probably just pick it because it's really, really close, and some engineers will work to like, three significant figures. 1.004 is equal to 1.0, and so maybe that's okay as a utilization ratio. But let's be a little bit more, ethical than that. So the 4500. Finally, if we come to a 250 by 101, we get 2620 as a compressive resistance. Is that okay? Yeah, that'll work, right? So we could pick a W250 by 101 at 2,620, which is bigger than what we need. How do I know that I'm satisfying slenderness by picking that section? How do I know that the KL over R ratio is small enough? Well, down here you're going to see no entries for some reason, right? So that's for W310, the smaller, the lighter W310s, there are no entries. What do you suppose it means if there's no entry in the handbook? Well, it means that for that effective length value, slenderness is not met. KL over R is bigger than 200. Okay, so you cannot not satisfy slenderness when you're picking sections from the handbook because, well, there's nothing there. Okay, this is the region where KL over R is greater than 200. So anything you pick will satisfy slenderness. How do I know that I'm satisfying local buckling? How do I know local buckling is an issue here, do you think? Well, from time to time, it's going to hit something. That's not the right watermark. Where is that? So sometimes there'll be little sections like this that have a little dash. Normally, that section means that it's class 4, and the handbook is already going to state the effective area for you. Okay, so local buckling is already included in these compressive resistance values. Picking something from this table, it means that local buckling has already been considered in the strength as well. Okay, so there's a available 250 by 101. It's got a compressive resistance of 2,620. It's there, so I'm satisfying slenderness. And the effective area, if I need to calculate it, is included in that as well. I'm not going to stop there, though, because maybe there's a lighter W310. Okay, so none of these W310s work. I'll turn the page, and I'll find the 450, 4500 line. I'll come across, and there's a 310 by 97 that has a compressive resistance of 2,820. That's bigger than for the 250 by 101. And what does it mean that this is 97? Is it heavier or lighter than the previous section? It's lighter. So it's stronger and lighter. That sounds like a good deal, right? Less steel. I can have a slightly more, conservative strength in there, right? It's bigger, but it's also lighter. That's going to make me feel a little bit better. I'm being economical, green, and I can sleep a little bit better at night because it's stronger than the other ones. But there might be a W360 that's better. Let's see. Well, there's none of them here. If we go to the next page, 4500, a W360 by 110 has a strength of 2,740. That's a little bit less than the W310 by 97, and it's a little bit heavier. So that doesn't sound like a good deal to me. What else is here? Nothing. Just heavier 360s, right, going all the way up to 1,086 kilograms per meter. If you wanted to throw that in your building, you could have a compressive resistance of 38,700. Feel pretty good about a utilization ratio of 0.1 or 0.07. So you're probably not going to do that, right? Please don't do that. You're not going to want to pick the heaviest section. Again, the goal here is to pick the lightest one. And just to remind us all here, the lightest one was the W310 by 97, and it was also the stronger of the sections that I'm considering there. Okay? Are there any questions about that process of picking a section that might work, that happens to be economical than other available sections in the handbook? Thank you. Okay, so we needed to pick something for an effective length of 4,500. I'm going to pick, right, so I'm going to use a W310 by 97. CR is equal to 2,000, whoops, that's not a very good 20. Right, 2,820 kilonewtons. Or a W250 by 110, I think it was, or maybe it was a 101. Yeah, it's 101. CR was equal to 2,620 kilonewtons for a W310, or sorry, 360 by 110. CR was equal to 2,700 and something, maybe 10 kilonewtons. I don't care that this, like if I was to calculate utilization ratio, right, this is going to have the smallest utilization ratio because it's 2357 over 2820. So the 310 by 97 is going to have the utilization ratio. And I said in lab before that you want to get utilization ratio as close to 1 as possible because that indicates that you're going to have a more economic design. You're making more efficient use of the steel. For compression, even for beams, that's not always going to be the case. The goal is to pick the thing with the least weight. And just because utilization ratio is better for this section than it is for the others, I don't care because I'm using less steel in that section anyway. Wider, and so the radius of duration, but the y-axis is bigger for a similar area that's slightly less than the others. Are there any questions about that example or anything else that we went through to get to this point before we wrap up lecture for the morning? Okay, well, now you should be able to identify which shapes make effective compression. There are square HSS sections, round HSS sections, and wide flange sections. You should be able to navigate the column selection tables in the handbook and use some of those tools to select the least weight section to satisfy the compression member limit states. Any questions about anything at all that we talked about this morning then before we call it a morning? All right, we'll see everybody then Friday morning.